this video, we're going to look at section 10.3. Now, 10.3 is going to be primarily review from your intro stats course. The only difference is when we look at these hypothesis tests, we're going to use the rejection region to conclude our test instead of using the p-value. But other than that, you're going to notice everything is pretty much the same as what you've seen before. So what we have here at the beginning, remember this was from chapter 8, and what we saw here is we've got some notation for some different target parameters, sample sizes, the point estimators that go along with those parameters, the expected value of the point estimator, and the standard error of the point estimator. And so all of these together, we're going to use these to help us with our hypothesis test. And so just as a note here, the values in the table are correct as long as we have independent random samples from the same population. So as a result of the central limit theorem, if the sample sizes are large enough, and remember large enough depends on what type of variables we're looking at and what type of point estimators we're using, then what it tells us, if the sample sizes are large enough, all of the point estimators theta hat are approximately normally distributed, and that's the point estimators that are given here in this table. There are of course other point estimators that we could come up with which are not normally distributed. So what we can do is we can standardize the estimator. So notice we've got the estimator minus the expected value divided by the standard deviation of the estimator, and we know this is going to have an approximate standard normal distribution, and we've seen this before. So what we can do is for any of the target parameters in the table, we can test the following hypotheses. And so notice these are hypotheses that are set up just like in your intro stat class. Here we're using theta and theta naught as just placeholders. So theta here will be a placeholder for the parameter that we're interested in, and then theta naught, that's a placeholder for the value that we're comparing theta to. So for example, we might want to find out if the population mean is greater than 10, then in the alternative you would have mu greater than 10. So these are just placeholders. And then the idea is we want to reject the null if the theta hat that we observe from our sample is large. And remember that having a large statistic or a large test statistic previously in your intro stat corresponded to a small p-value, so that's why we would reject when the p-value was low. Well, here instead of defining things in terms of the p-value, we're going to find the cutoff that tells us if the estimator is large or not. So notice if the null hypothesis is true, in other words, assuming that the null hypothesis is true, what we're going to do here is we're going to standardize our estimator based on the value of the parameter under the null hypothesis. Because recall, for a hypothesis test, we always assume that the null hypothesis is true. And so what this is going to do for us is this tells us how to expect the parameter, or probably the estimator rather, to behave when the null hypothesis is true. And then we're going to define when our estimator is too extreme under that assumption. And so we know that this is going to have a standard normal approximation. And so this is the test statistic that we are going to use. This is the exact same test statistic that you used in your intro stat course. So for example, in your intro stat course, you may have looked at x bar minus mu naught divided by sigma divided by the square root of n, or you may have had an s there instead of sigma and used a t instead of a z, but it is the exact idea. Same idea. We've got the estimator, the mean of the estimator under the null hypothesis divided by the standard error of the estimator, again assuming the null is true. And so what we're going to do is for any specified value alpha, we can find C, and recall that alpha is equal to the probability of a type 1 error, and then our rejection region will be equal to Z greater than alpha, or Z alpha rather. And so the idea here is that once we standardize our test statistic, we know that it's centered at 0, or its distribution is centered at 0. So what we're going to do for a right-tailed test is we would put alpha area, and then our cutoff is equal to this endpoint right here. And if our test statistic ventures into this region, we know that it is extreme, and therefore we will reject the null. Notice that would be the exact same thing as the p-value being less than alpha. So again, same thing you did in your intro stat course, it's just a different way to look at it. So let's look at an example. All right. A sociologist claims that the average number of people per family unit in a large subdivision is higher than the national average of 4.7. He interviews 100 families, obtaining a mean of 4.8 with a standard deviation of 0.80, and we're going to test his claim using alpha equals 0.1. Well, first of all, notice here, let's identify some of the information. This is our sample size n. We know here that this is x bar. And then this value here is S. And then this is the national average, so this is going to be what we're comparing our mean to. All right, so let's set up our hypotheses here. Another thing to note while we set up our hypotheses is our sample size was large. We had a sample of 100, so it is appropriate to assume that the central limit theorem is going to hold. So what we're going to do is we're going to try to test his claim. And notice he claims that the average number of people per family unit in a large subdivision is higher. So higher is going to be our key word here. In other words, we're going to try to prove that the population mean is greater than the national average of 4.7. And then under the null hypothesis, we're going to have that mu is equal to 4.7. All right. Now we could calculate our test statistic. Notice that z is equal to y bar minus mu naught divided by sigma divided by the square root of n. Now for this particular example, we do not know the value of sigma, we just know the value of s. So we are going to approximate this by y bar minus mu naught divided by s divided by the square root of n. Now, in your intro stat course, you learned that if you make that approximation using S, we could also use a t-test statistic, which might be a better choice. But since our sample size is large here, we know that there's going to be very little difference between the t and the z, so we're going to proceed for now using the z distribution. Next, we're going to fill in these values. I've used an x bar up here, but it doesn't matter. We could switch that over to y bar. It's the same, just notation. So we know that y bar is equal to 4.8. The value under the null hypothesis is 4.7. Our sample standard deviation is 0.8. And then we're going to have the square root of 100, which is our sample size. And if you put that in your calculator, double check, but you should get 1.25. So let's look at what this is going to mean in terms of the sampling distribution of z, assuming that the null hypothesis is true. Well, under the null hypothesis, our test statistic will follow a standard normal distribution, which is centered at 0. And notice here that we're using alpha equal to 0.1. Well, since alpha is equal to 0.1, and this is a right tail test, what I'm going to do is I'm going to put area 0.1 in the right tail, and what I want is this endpoint right here. So to find that, we're going to get our calculator. Get a little more light in here. So if we go to second vars, which will give us the distribution, and what we're going to look for is the inverse norm function. Now remember, your calculator requires the area to the right. If I have the area to the left. If I have 0.1 to the right, that means to the left I have 0.9. So I'm going to give my calculator area 0.9. And we are working with the standard normal distribution, so I'm going to leave that as a 0 and 1. And notice this gives me the endpoint 1.28. And so my endpoint here is 1.28, and this is going to help me find my rejection region. So my rejection region is going to be if my test statistic z is greater than z of 0.1, which we just found was 1.28. So if my test statistic is larger than 1.28, I'm going to reject. But notice that my test statistic was 1.25. So since 1.25 is less than 1.28, we fail to reject the null. And so notice what this tells us is at the 10% significance level, there is insufficient evidence to show that the average number per family unit in a large subdivision is higher than the national average of 4.7. So again, really the only difference between this and what you did in your intro stat course was in your intro stat course you would have found the p-value instead of finding the rejection region. All right, we have another example here. This one says a real estate agent claims that at least 75% of retired couples prefer living in an apartment or a condo to owning their own home. Of 200 retired couples, 165 prefer living in an apartment or a condo. So first of all, notice here, this example, we're not working with a mean, we're going to work with a proportion. And so let's summarize some of that information. Notice that n in this case is equal to 200, and our statistic p hat is equal to 165 divided by 200. All right. Also notice that we have 165 that preferred living in the condo, and that also tells us that we have 35, not 135, just 35 that did not prefer to live in an apartment or a condo. Both of those numbers are large enough that the central limit theorem is going to apply. Also notice in this case we're trying to decide or test the claim rather that at least 75% prefer living in the apartment. So in other words, we have another right tail test and we're testing to see if p is greater than 0.75, and under the null p is going to be equal to 0.75. Now just like you would typically do with a hypothesis test, we can now calculate our test statistic. So in this case, our test statistic is going to be equal to z is equal to p hat minus p naught divided by sigma p hat. And I just realized that I made a mistake earlier when we talked about whether or not the central limit theorem applied. When deciding if the central limit theorem applies for hypothesis test, we're not looking at the actual counts that we find. Recall that we typically are looking at the expected number of counts assuming that the null hypothesis is true. So in other words, if we spoke to 200 people, assuming that p was equal to 0.75, is our sample size large enough? So assuming that p is equal to 0.75, if we take 0.75 times 200, that's going to give us 150. And 1 minus 0.75 times 200 is going to give us 50. Both of those values are large, and that is why the central limit theorem is going to apply here. All right, back to our test statistic, plugging in these values. And notice when we calculate sigma p hat, this would typically be equal to the square root of p times q divided by n, but we don't know what p times q is, so what we do is we're going to estimate that using the value of p under the null hypothesis. And again, that's because in hypothesis test, we're always assuming that the null hypothesis is true. So if we estimate these using the value under the null hypothesis, we're going to get 0.75 times 1 minus 0.75 divided by 200. And if you put that in your calculator, I believe that is 2.4495. So next, we need to find our rejection region. And what I would like to do for this example is I would also like you to find the p-value. And I want you to see that these two correspond. So the rest of this problem I'm going to leave as the quiz for this section. So what you'll want to do for the quiz is I first want you to conclude the test using the rejection region. So in other words, using the rejection region method, what is your cutoff and will you reject or fail to reject? Then I'd like you to do what you did in your intro stat course and find the p-value. And based on the p-value, will you reject or fail to reject? And what you should find is whether you use the rejection region or you use the p-value for this example, you're going to reject the null. And then at the end, I'd like you to conclude the hypothesis test. All right. Moving on to page 8. So note, for any of the target parameters in the table, we could also make the test a left tail test. So we've just looked at right tail test, but we could also have a left tail test. In order to do this, we would use the exact same test statistic, but in order to find the rejection region, we're going to look at the lower endpoint instead of the upper endpoint. We could also do a two-tailed test as well. So let's look at kind of our summary here. So notice here are our 3 different types of hypothesis tests we could have: the right tail, left tail, or two-tail. All of them are going to use the same test statistic, but how you find the rejection region will be based off of which style test you have. So kind of looking at a picture, what we're saying here, if here is a standard normal distribution, for an upper tail test, you're going to put alpha area, and this is going to give you the cutoff for an upper tail test. Whereas if you had a lower tail test, we would put alpha down here, and this endpoint would be the cutoff for the lower tail test, or we could call that a left tail test. And then in the case where we have a two-tailed test, what we do for a two-tailed test, and I'll draw this one up here at the top, for a two-tailed test, what we do is we put alpha divided by 2 in either tail, and you're actually going to get 2 cutoffs. And what you look at is you're looking to see if your test statistic falls below this cutoff or above this cutoff. Now, due to symmetry, that's the same thing as saying if the absolute value of the test statistic falls above this cutoff. And then note here, it's better to use a one-tail test if you can, because they generally are more powerful. However, you should not look at the data to decide which one tail to use. So in other words, you need to make that decision before ever looking at your data if you really are just interested in the one tail, whereas if you're really interested in a two-tail, then you need to perform the two-tail test. And then let's look at one more example. So this one says, Two randomly selected groups of citizens were exposed to different media campaigns for a political candidate. 1 week later, the people were asked if they would vote for the candidate. And here are our results. So notice along here we've got the number in the sample, so in other words N1 and N2, and the number who would vote. So notice this is going to be a difference in proportions that we're interested in. And so what we're going to do here is we're going to test to see if there's a difference in the effectiveness of the two different campaigns. All right, so the first thing we're going to do is set up our hypotheses. And notice for this example, we're going to look at, again, a difference in proportions. So we're going to call the conservative campaign group 1 and the moderate campaign group 2. So under the null hypothesis, the proportion would be the same for the two groups. And notice we're looking to see if there is a difference. So under the alternative, we're going to have P1 not equal to P2. And again, if we look here for each of our groups, the number who would vote for, we've got 60 and 90. And then if we take 150 minus 60, we're going to have 90, and 180 minus 90 is 90. All of those counts are sufficiently large, so the central limit theorem does hold here. All right, next thing we're going to do is calculate our test statistic. So again, everything we've done this chapter, with the exception of defining the rejection region, you've done all of this in your intro stat class, so it should all be review. So recall that your test statistic in this case is p hat 1 minus p hat 2 divided by the square root of pq divided by n1 plus pq divided by n2. Well, that's going to be equal to p hat 1 minus p hat 2 times the square root. Notice both of these are multiplied by PQ. We don't have PQ in this case, so instead we're going to estimate that with P hat times Q hat times 1 over N1 plus 1 over N2, where P hat, that pooled proportion, is equal to the counts in each of the groups divided by the two sample sizes added together. So for this example, notice that P hat is going to be equal to 60 plus 90 divided by 150 plus 180, which is equal to 0.4545. P hat 1, the proportion of successes from the first group, is 60 divided by 150, which is equal to 0.4. Oops. And P hat 2 is equal to 90 divided by 180, which is equal to 0.5. Alright, so now we can fill in our test statistic. So our test statistic in this case is going to be equal to, we're going to have 0.4 minus 0.5, and then in the denominator we're going to have 0.4545 times 1 minus 0.4545 times 1 over 150 plus 1 over 180, and I get that's equal to negative 1.8166. So next we need to find our rejection region, and notice this is a two-tailed test. So if I draw my standard normal curve, notice here we're using alpha equal to 0.01. So what I'm going to do is in each of the tails here, I'm going to place 0.01 divided by 2 area. In other words, 0.005. And what I want to do is I want to find the endpoint that corresponds to that. So I can use my calculator again. So notice that this endpoint here has 0.005 area to the left of it. So again, going to my calculator, I'm going to hit second distribution. I'm going to use that inverse normal function, but now I want area 0.005 to the left. I'm still working with the standard normal. and I find this is equal to negative 2.576. So this endpoint is negative 2.576. So I know by symmetry the positive endpoint is 2.576. So if the absolute value of z falls either above this value, or we could just say if z falls below or above this value, that would be the same thing, then we are in the rejection region. So notice our z value does not fall outside of the cutoffs. So for our rejection region, if the absolute value of z is greater than the upper endpoint, this is the same thing as saying if the absolute value of z is greater than 2.576, then we would reject. So notice in this case we are going to fail to reject because that was not the case. So what we can say here is there is insufficient evidence to conclude that the proportion of people per family, proportion of people who prefer the conservative media campaign for a particular political candidate differs from the proportion of people who prefer the moderate media campaign. And this is going to conclude the section 10.3 notes.